Hi. The root and ratio tests are two twin tests to discuss convergence for numerical series. Very popular among students because of the ease of use. However, applying these tests is not error-free, so it is very important to know what they state, why, and what are the limits of their use. In this video, we present both tests, together with some of their features, and we apply them to some examples. Let us start by saying that both tests apply to series with the terms of constant sign. So to fix ideas, we will consider series with the terms of positive sign. Now, the root test is based on the idea that if the series of an looks like a geometric series, sum of powers of a number q, then the value of q will determine convergence of the series. So the idea is that since here we have a positive term, series q will be greater or equal than 0, and therefore we will have convergence for q strictly less than 1. But how can be computed such a q? Now, again, the idea is that if an looks like a q to the power n, when we take the nth root of an, this should be like q. So this is the idea behind the test. And let's see a precise statement. So we assume to have a sequence an of positive terms such that there exists a limit of their roots and roots for n going to plus infinity. We call this limit q, and since it is a limit of positive quantities, it will be greater or equal than 0 and potentially equal to plus infinity. So it will vary in this range, 0 to plus infinity. Now, the theorem says that if that q is strictly less than 1, then the series of an is convergent. If q is strictly greater than 1, the series of an is divergent, and moreover, an goes to plus infinity. But if q is equal to 1, the test cannot determine whether the series converges or diverges. This last point deserves some reflection. There are cases where q is 1 and the series converges, and cases where q is 1 and the series diverges. So we say that basically the test fails. Let's illustrate this phenomenon on a couple of examples. Here we consider a divergent harmonic series, the sum of fractions 1 over n. We apply the root test to the term an equal 1 over n. So the nth root of this is 1 over n to 1 over n. And to compute now this limit, we have to be careful because it is an indeterminate form infinity to 0. However, by using properties of exponentials and logarithm, we rewrite this as 2 to log base 2 of the same quantity. And taking down this exponent, we get easily this. 2 to exponent log base 2n divided by n. This is a comparison between log and power. The power wins, so the fraction goes to 0, and the exponential goes to 1. So here we have q equal 1, and the series is divergent. Let's now consider a convergent harmonic series as the sum of 1 over n squared. Now you notice that these are just the squares of these. So when we compute the nth root of these terms, we have the squares of the old nth root. We already knew that this goes to 1, so this will go again to 1. So here we have q equal 1, and the series is convergent. The moral is that for q equal 1, nothing can be concluded. Let's see now how the test can be applied on a simple example. So here we have the series n cubed times 2 to minus n squared. They are clearly positive. We take an and we do the nth root of this to power 1 over n. So this is n cubed to power 1 over n. So we multiply exponents, and we write n to exponent 3 over n. And the same for the exponential 2 to minus n squared to 1 over n gives 2 to minus n. Now this is the quantity n to 1 over n we discussed a minute ago that goes to 1 cube, so it will go to 1. And this exponential goes to 0. Therefore, we conclude that this limit exists, and it is equal to 0. This is the number q we are looking for. So the root test applies, and this series is convergent. The ratio test is practically identical to the root test. The only slight difference is that it applies to strictly positive series, because we have to compute the limit of fractions, ratios between two consecutive terms, and we cannot take an an equal to 0. So it says that suppose that there exists a limit when n goes to plus infinity of the ratio an plus 1 divided an. Let's call q that limit. Since the limit is limit of positive quantities, again, it will be in the range from 0 included to plus infinity included. Well, the conclusion is the same. If q is strictly less than 1, the series of an is convergent, while if q is greater than 1, strictly greater than 1, then the series of an is divergent, and moreover, an goes to plus infinity. The case q equal 1 yields to the same discussion we have seen for the root test. And exactly the same examples can be used here also to prove that you can have q equal 1 with this limit for a convergent and for a divergent series. So in other words, the test fails. Now let's see the application of this test on a series like this one, sum for n going to 1 from 1 to plus infinity of n to the n divided 3 to the n times n factorial. As you can see, since n is greater or equal than 1, these numbers are strictly positive. So now we calculate the ratio an plus 1 over an. So to compute an plus 1, we have to replace n by n plus 1 here. So we get n plus 1 to power n plus 1 divided 3 to exponent n plus 1 times factorial of n plus 1. And now instead of dividing by an, since an is a fraction, we multiply by the reciprocal. So 3 to the n times n factorial divided by n to the n. Now we simplify as much as we can. For example, you see that 3 to the n disappear here and here. Then we have this factorial that we can simplify with the denominator, because the factorial of n plus 1 is n plus 1 times n factorial. So we can cancel this n factorial. And you can see that there is an n plus 1 here and here. So we can just simplify this to eliminating this plus 1 here. So at the end, there is nothing more to be simplified. So we end with 1/3. This 3 comes from this exponent 1 times the nth power of n plus 1 divided by n. So n plus 1 divided by n can be also written as 1 plus 1 over n to the n. Now here we recognize the well-known remarkable expression that yields the limit of number e. So when n goes to infinity, this goes to e divided 3, and that's our q. Now, since e is well known to be strictly less than 3, this number will be strictly less than 1. And that's why the ratio test applies, and we can say that this series is convergent. That's it. So what are the next steps? First of all, you should practice the application of root and ratio tests to exercises like these ones. A very frequent question is the following: which of the tests should I use? Well, there is not an answer to this question. The unique honest answer is that you should use the test for which you can compute the limit. So the limit of an to 1 over n in the case of root test, and the limit of an plus 1 divided by n in the case of ratio test. Also, it is useful to know that when one of the tests fails, also the other one will fail. So when you get q equal 1 in the test of the root or the ratio, you will get q equal 1 also in the other test. So for example, if you get q equal 1, it is not wise to try to apply the other test, because you will get the same answer. For a deeper understanding, as usual, you should try to solve a little bit more abstract problem. An example could be this problem. So good luck.